In this video, we're going to take a look at mathematical induction. Our approach will be to first show that the statement holds true for some natural number n. 2, we'll assume that the statement holds true for some natural number k. And third, we'll evaluate the statement at k plus 1. If the statement holds true, then we know that the statement will also be true for all natural numbers n. In this example, we'll be looking at the statement 10 plus 20 plus 30, a sequence which ends at plus 10n, is equal to 5n times n plus 1. This particular sequence happens to be an arithmetic sequence. This is evident because the difference between one term and the next is a constant. Let's get started with step 1. In step 1, let's let n be equal to 1. Then we have, on the left, 10 times 1 equal to, on the right, 5 times 1 times 1 plus 1. Note that we simply substituted 1 for each n in our statement. Simplifying the statement, we get 10 equals 5 times 2, or 10 equals 10. So now we see that our statement holds true for some natural number n. For step 2, we'll assume that the statement holds true for some natural number k. So we'll say assume true for some k that is an element of the natural numbers. So evaluating our statement at k, we have 10 plus 20 plus, and we don't have to write all of the sequence because of course this sequence could go on to infinity. So we write our little dots or ellipses, and then plus 10k, replacing n with k, equal to 5k times k plus 1. So in this step, we're simply assuming that the statement is true for some k when we replace n with k, where n and k are both elements of the natural numbers. Moving on to step 3. We evaluate the statement at k plus 1. And here is where we need to be careful. On the left-hand side, we begin by writing our initial left-hand expression. So we have 10 plus 20 plus, and then our ellipses, plus 10k. Now, in addition to this, we add plus 10 times k plus 1. This becomes our new left-hand side of the equation. And I'll note here, this is our left-hand side. We set this equal to our right-hand side, which we write as follows. 5 times k plus 1 times k plus 1 plus 1. This is our new right-hand side. Our job is to simplify the left and right-hand side and show that they are equivalent, or in other words, that our statement holds true. When we do this, we will complete our proof. So let's get started. First, I'm going to work on simplifying the left-hand side. Note that in the original statement, we can see that 10 plus 20 plus 30, which we actually ended up not using, and that's okay. It's assumed to be part of our sequence, plus 10n is equal to 5n times n plus 1. This means that we can substitute this part of the left-hand side with the statement 5n, or rather 5k times k plus 1. Now we add our 10 times k plus 1, and we use our basic rules of algebra to simplify. Our distributive property gives us 5k squared plus 5k plus 10k plus 10. This becomes 5k squared plus 15k plus 10. Okay, so we make note of our simplified left-hand side of the equation, and now we move on to simplifying our right-hand side. Recall that the right-hand side evaluated at k plus 1 was 5 times k plus 1 times k plus 1 plus 1. Again, using basic rules of algebra, we'll simplify 5 times k plus 1 times k plus 2. Let's go ahead and FOIL our binomials using the distributive property. So we have 5 times k squared plus 2k plus 1k, which gives us 3k plus 2. Now, distributing our 5, we have 5k squared plus 15k plus 10. Once we've distributed the terms on the right-hand side, we get 5k squared plus 15k plus 10. Looking back, we can see that this is the same as our simplified expression on the left-hand side. Therefore, since the condition of our statement evaluated at k plus 1 holds true, we know that our statement is true for all natural numbers n. This completes our proof and concludes the example. I hope you found it helpful, and we'll see you next time.